Hey, what's up? What am I doing up here in this corner? I should be down there. Oh well, we'll make it work. Okay, I'm in a new territory, uh, and so are you. You are in. You're about to enter a world of infinity, but not beyond. No, no. We got to figure out infinity first. We can't go beyond infinity. You sane? Saying Buzz Lightyear. I don't see him around anywhere. You are getting ready to enter a really weird zone of mathematics. The study of infinity and infinite series, and it's a little mind boggling. So make sure you pay attention. Make sure you know the truth behind infinity, that it's difficult. It's difficult to figure out. So you need a healthy respect for infinity. You need to know that you can figure out some things, but there are just some things that will just not make sense. You need to be okay with that. So you need to be able to talk about sequence convergence. We looked at that last week with the ideas of using L'Hopital's rule and just some intuition mathematically, like a sequence converges if it pinches down to a single number. If it goes to infinity or the values bounce back and forth, that's divergence because they don't pinch to a single number. So we're going to be talking about sequences today. And then you have to be able to add stuff together. Like, that's what a series is, right? I mean, series add things together. Maybe. We'll see. Okay. So this whole chapter, this whole big idea 6, right? We're getting ready to launch into. We're gonna study this main question here. Okay, so does the series converge or diverge? That's going to be the big question for the next couple of weeks. Now, what you might want to ask as a follow-up is, if the series does converge, well then what does it converge to? I mean, inquiring minds want to know. That seems like a very interesting question. Well, there's going to be some times where we can answer that second question. In fact, I'm going to answer that question today. We're going to look at geometric series. We're going to look at telescoping series. And those are the only 2 types of series that we're really going to mess around with figuring out the answer to that second question. Taylor series, but they're coming. They're off a little ways. So we're going to mainly focus on, does the series converge or diverge? And we're going to have a list of tests, a list of mathematical tests that we can run to see whether a series converges or diverges. All right. So just leading off, you might want to define what a series is, right? So what is a series, right? Before we jump in. And you might know that a series is the sum of the terms in a sequence. That's right. I mean, you studied arithmetic series, geometric series a few years ago. But really nothing else. Here we're talking about infinite series. So we're going to be adding up terms that never stop. And we're going to see whether those converge or diverge. Do they grow? So do they pinch to a number? Do they just keep growing? Do they bounce back and forth? Well, we got to know what a series is. So you may think that a series is the sum of the terms in a sequence. And you are correct, but you're wrong. Actually, a series is a sequence of partial sums. Very important to know that a series is actually a sequence of partial sums. Now, let me explain what that is. Okay, so let's think about this series here. The series, just adding up the counting numbers, 1, 2, 3, 4, 1 plus 2 plus 3 plus 4 plus 5, all the way up to the finite number n. So what we want to do is we want to look at this as the sequence of partial sums. So here you see the list of all of these things. So if I just add up the first term, I get 1. Doi. If I add up the first 2 terms, 1 and 2 make 3. I add up the first 3 terms, 1 and 2 and 3 make 6. And 1 and 2 and 3 and 4 make 10. And then add one more term and it's 15. So S sub n denotes the the sequence of partial sums. So we're partially adding the sums up to a certain part. So if we could write the nth partial sum, could we come up with a formula that describes, an explicit formula that describes S sub n as a sequence? And you might remember, or you might know, that there's a formula for adding the first n numbers. The whole Gaussian formula, right? Like adding the numbers 1 to 100. Well, there's a formula that links the sequence 1, 3, 6, 10, 15. They're called triangular numbers. And the explicit formula for that, check it out down there, is n times n plus 1 over 2, right? Adding the first and the last term, n plus 1, and then figuring out how many pairs of numbers add up to n plus 1. So the sequence of partial sums can be explicitly defined as n times n plus 1 over 2. Now, we can kind of confirm that at infinity, obviously, n times n plus 1 over 2 is going to get infinitely large as n drives off to infinity. So we would look at the sequence of partial sums, then do what we do with a sequence, trying to find what the sequence converges to, send the limit to infinity. Clearly, that would be infinity. Or negative 1/12. Stay tuned. I'll put up a bonus video for that. So it's clear that this series diverges, right? It goes off to infinity. But what about this series? All right, what about 1 over perfect squares? What about the reciprocals of all the perfect squares? Now this series seems like it seems like I'm going to be telling you that it converges, right? Like that's what math teachers do, right? They show you one thing and then they show you the other way around. Well, I'm not going to say that I am. I'm not going to say that I'm not. But if we think about 1 over n squared and add 1 to 1 over 4 to 1 over 9 to 1 over 16 to 1 over 25, and if we add up all of the reciprocals of every single square number off to infinity, will that converge to a value, or will it just keep on getting infinitely bigger? I mean, you might want to say that it converges because they're getting really, really tiny, but that's a dangerous place to be. Maybe we ought to take a look at the partial sums, right? A series is a sequence of partial sums. So on this table, I'm going to do the same treatment as I did before and just figure out what the partial sum is. So S sub n is just the finite partial sum from 1 to n. So if I add up the first number, right, that would just be 1. So S sub n is 1, right? If I add up the first 2, that's 1 1/4, which is 5/4. All right. So continuing the table, you see all the numbers down there. They just get all crazy. Like I had a whole lot of fun figuring out those rational numbers there. So if you skip a few and get to n, and can you figure out an explicit formula for 1 plus 1/4 plus 1/9 plus 1/16 all the way up to plus 1 over n squared? Let's look at that sequence. 1, 5/4, 49 over 36, etc. I hope those numbers are right. I'll keep going and coping. Can you figure it out? Because I can't. I don't know what an explicit pattern for that would be. Now, here's what you're thinking. You might have to. You might think that you have to come up with this sequence of partial sums, but the truth is you don't. You absolutely do not have to come up with this partial sum sequence. What you need to know right now is that to truly talk about a series, we have to define it as a sequence of partial sums. That is important. So here's where things are going to get a little bit screwy, and you're going to have to follow along. Okay, so if a sequence of partial sums converges, then the series also converges, right? That makes sense, right? Because the series and the sequence of partial sums are exactly the same thing. So if a series is going to converge to a value, then it's got to be necessarily true that the values that we add, the individual values that we add, have to be approaching zero, right? I mean, that makes sense, right? Because as we approach a certain convergent value for the series, the difference between each of the individual terms has to be getting really, really tiny. So if we say that a series converges, then it's necessary that the individual terms are getting closer to zero. It would make more sense to think about it if they didn't approach zero, right? So if we had to add the numbers, right, in this series here, if we added the numbers from 1 to infinity of n over n plus 1, it's clear to see that the terms, the individual values, are approaching 1. So that means that if you could graph out the sequence of partial sums, it would almost look linear by the time you got out to infinity. The common difference is going to be 1. Well, clearly that's going to go off into outer space, increasing by 1 or close to 1 every time you added another number. So if the sequence values, the individual terms of the series, if they don't go to 0, then it's obvious that the series must diverge. Okay? So if you knew that a series if you knew what the sequence of partial sums was, like here, take a look at this next one. If the partial sums, if the sequence of partial sums, S sub n, can be denoted as n over n plus 1, if that's the sequence of partial sums, aka the series, then that series and sequence of partial sums both converge to 1. That means we know the individual values of this A sub n sequence, the individual terms of the series. That means they have to be going to 0. Hopefully that has made sense. Now, if we know that the sequence values are approaching 0, so if we look at a series and we see the individual terms, how they're getting super, super tiny, what would that tell us about the series? It might converge, but it might not. It feels that you need to fight the urge to say that a series converges only based on the fact that the individual sequence terms converge to 0. That is a dangerous place to be, and don't be that basic. Don't just think it boils down to the sequence going to 0 or not going to 0. It's a whole lot more than that. Okay, you're going to see how it's a dangerous place to be. So here is our first big test. It's called the nth term test. All right, we know that a series is a sequence of partial sums, and from the information we've gathered on the big discussion above, here is an nth term test that tells us that if the limit of the sequence is not 0, then the series, the infinite series, must diverge. That is truth. That is called the nth term test. Now, that's an if-then statement. So there are other ways to spin that if-then statement. One of which is called a contrapositive. Now, the contrapositive would say this: if, in blue down there, if the series converges, then the limit as n goes to infinity of the sequence approaches 0. That's always logically true. Contrapositive is always logically true to an if-then statement. So the nth term, we got the nth term test, but then its contrapositive is also true, there in blue. It's the inverse that is dangerous. Okay, so the inverse of this conditional statement would say that if the limit of the sequence is 0, then the series converges. That is the inverse statement, and it's not logically sound. Okay, if the limit of the sequence is 0, then all we know is the series has a possibility to converge, but it still could diverge. Heck, we don't really know anything at all. We only know that the sequence goes to 0. That's it. So be careful how you apply the nth term test. Apply it the correct way. Don't fall prey to these other blunders of the nth term test. So I'm going to show you a few examples here of using this nth term test. Okay. So here are 3 examples. All right, so let's take a look at the red one first down there. All right, so the series, the infinite series from 1 to infinity of 2n over 3n plus 1. Now the values get smaller, right? I mean, because the denominator is growing faster because we're multiplying by 3 every time instead of just 2. But if we take a peek at the individual terms of the sequence, 2n over 3n plus 1, we see that the limit of that sequence is 2/3. Well, if the limit of the sequence is not 0, then the nth term test proves that the series will diverge. Just like adding 2/3 an infinite number of times to its 2/3, 2/3, 2/3, it's going to be a linear growth and it's going to diverge. Let's take a look at the green one. Okay, so the green one there, adding the terms infinitely of the sequence n sine of 2 over n. Now, n sine of 2 over n, if you're curious as to what that does, well, let's just see what that does at infinity. Well, the limit as n goes to infinity of n sine of 2 over n through the power of L'Hopital's rule, you could confirm that that limit is 2. I won't show you L'Hopital's rule. You know L'Hopital's rule. We covered it in a former video. But that limit is 2. So what does that tell us about the series? Well, if the sequence doesn't go to 0, which 2 is not 0, then we know that the series must also diverge. Let's take a look at the last one, okay? The one we were figuring out before, 1 over n squared, the sum of all the reciprocals of every square number off to infinity, right? What does that do? Well, let's look. 1 over n squared as a sequence, right? It trends to 0. So the limit as n goes to infinity of the sequence 1 over n squared is 0. Now be careful. What does the nth term test say about that? Nothing conclusive. If the limit of the sequence is 0, we don't know jack diddly squat about the series. We're going to need another test to prove convergence or divergence. So stay tuned. We'll talk about that later. Okay, you've learned your first test for showing series convergence. It's called the nth term test. Now go practice with it. Enjoy.